So now we'll look at some specific applications that involve working with this equation that we now know. The fundamental idea is that the rate of change is proportional to the amount present. So one place that happens is continuously compounded interest and investments. All right, so for some people who have done a little work with continuously compounded interest, you know that for continuously compounded interest, we're going to use A of t to represent the amount in the account, and then we're going to use A0 to represent the initial amount in the account, and then typically we use R for interest rate. But so the R of interest rate in this applied problem is the K of this general, like what we're really showing is how many different things flow from this general solution to actually it's a particular solution to the, but it's a generalized by the fact that the K we didn't really specify. It's really the Y0, like we didn't specify. Anyway, I won't go down that rabbit hole either. It's a generalized particular solution to a differential equation that has all these applications to different situations. So many people learn this equation as just A equals P e to the RT. So these are just sort of permutations of ways that you can write that. Here P stands for principal. That is the initial amount that you invest, and it is essentially Y0, or the initial amount in an account. All right, but here's the thing. It also describes investments. So it doesn't have to be a continuously compounded interest. It also describes general investments. So assuming that my growth rate remains constant, and of course that's always the trick in investing. Is your growth rate going to remain constant or not? You can only predict over the short term because the growth rate is actually constantly changing, but you can make some kind of predictions. So let's say I had, I didn't write this yet. I'm just going to write this ahead of time. Okay, so I'll write it now. It'll be sloppier than I intended. A company that is valued at 1.47 million yen or dollars or whatever, maybe pesos, I don't know, in 2018 is worth 2.38 million in 2021. All right, so assuming constant growth, assuming a constant rate of growth, so we continue growing at the same rate, which a mathematical way of saying assuming a constant rate of growth would be to say that dy dt equals ky. And a lot of times in the AP exams, they'll sort of start the question with this statement. Something goes by dy dt equals ky, and your job is just to recognize that you essentially have then y equals y0 e to the kt. All right, so now our job is going to be predict the value of the company in 2025. All right, so what we want to do is, we don't want to have to solve that differential equation every time. So essentially what we're learning here is that this is another way of saying, my purple pen is still dead. This is another way of saying that y0 equals y equals y0 e to the kt. It's another way of saying that. Or more particularly to the context of this problem, usually we would say I'm going to write it this way, a of t equals a0 e to the rt. All right, so what we've got here is that we were given a value at two different times, and using a value at two different times, we essentially solve for the rate, and then we get, once you got this equation, basically they're going to give you values that you can plug into the equation and solve and get other things. Everything else is just algebra from this point on. So I guess in this case what I would do is say, remember you can play around with the definition of how the t is going to be. I'm starting at 2018, so why don't I make that t equals 0? Right, t equals 0 is arbitrary. So we'll let t equal the year minus 2018. That way 2018 is t equals 0. All right. So then our value of 1.47 in 2018 is really saying that a of 0, which is the same as saying a sub 0, is 1.47. We'll leave the millions off and we'll just stick that on at the end. All right, and then this information here, then 2021. Okay, so 2021 is going to be t equals 3. All right, so 2021 is t equals 3. So then we can say that what we're really saying here is that a of 3 is equal to 2.38. So then I can just use the equation a of t equals a0 e to the rt, and we'll use that. We'll use this known piece of information to solve for r. All right, so then we can say that 2.38, right, that's our a of t, is equal to our a0, which is 1.47. E to the r is going to be unknown, but our time that has elapsed is 3. All right, so you solve that using logarithms. I just solved it without getting intermediate values. That way I could just stick it all into the calculator at the end and get 3r equals ln of 2.38 over 1.47. Remember how to solve exponential equations. So r is equal to 1/3 ln of 2.38 over 1.47. All right, so that's that. And then, by the way, that turns out I did it on my calculator. It's probably still in here. It's about 0.16061. It's right there. Right. So I just put those numbers in the calculator because one thing to know in terms of any kind of application, whether it is financial or engineering, e to the x is a very sensitive function. All right, exponential functions grow very rapidly. That means if I make a very small change in the t, or if I get the r slightly wrong, I'm going to end up with a huge difference in outcome. So I'm going to write down 5 decimal places here, 0.16061. But when I go to actually calculate it, I'm going to use the values in the calculator because that will be even more accurate. All right, so using this r now, I can say what a of t is. A of t as a function, right? So coming back to a of t equals a0 e to the rt, I now know both a0 and r. And this is how it works. You use given information to pull out the constants that you need for the equation. It's all algebra. You've probably done it before. So my a0 was 1.47 e to the, and now I know that r is 0.16061, 0.16061 t, right? So that's basically using this equation with my known values of a0 and r. And then it's a simple matter of saying that the year 2025 is going to be t equals what? So that's 7 years after 2018, so it's t equals 7. So I'm really looking for a of 7, which is 1.47 e to the 0.16061 times 7. So I can write it with the 5 decimals here, but when I actually go to calculate it, I'm just going to put it into my calculator, having copied this number down into my expression. Right, and so I get 4.52, and now I'll round it to the same 2 decimal places in which the problem was stated. So I'm going to say that that equals about 4.52, and I'm going to say the value of the company is about 4.52 million. So the value is 4.52 million. All right, so that's basically just some algebra, and that's an example. Okay, next up, we're going to look at some one example involving half-life, which is an important application, and then we'll go on to hopefully the logistic equation.